increment along the orbit of the function. So take function, point x, then take the orbit coming out of this point, and take increment along this orbit. So it's well defined because the function, you're remaining on this surface, you define this increment and divide this by the length of your orbit between x and this point. So you define everything correctly now. So this way you define and then go to the limit when h goes to 0. And you will get it is the same as you insert here the orbit and take derivative along the orbit. It's the same as this definition. So this is the, conclusion. You can define on the surface the derivative only along the tangential vector fields. If you want to define derivative, you should have tangential vector field for this. Okay. So the differential operators on the surfaces are defined along the tangential vector fields. Okay, now we have concrete vector fields which we can use for the definition of our derivatives. So those are called Günter's derivatives. Günter, why Günter? Günter was some mathematician, mechanist of German origin, but living in Soviet Union, as many Germans living in Soviet Union, in Russia. And he wrote a book about, it was about the problems of elasticity and in 30s, and he used first these derivatives, Günter's derivatives. So he found very simple vector field which can be used to define this derivative, and used it in some problems. And we now use these the differential operators to define all kind of differential operators on the surfaces, and it turned out very useful. It was, I initiated to consider these vector fields in 2003, and then we have done this work with two Americans working in the United States, this Marius Mitria and Dorina Mitria. We developed the calculus of these differential operators on the surfaces, and they turned out very useful. You will see how they simplify the consideration of boundary value problems on the surfaces and so on and so on. And why we need all this, I will tell you also. Oh, the time is running very fast. I have 1 hour, yes. So Günter's derivative. Günter's derivative is defined very simply. You take the normal vector field and define the normal derivative. It's here. You take the components of your normal vector field, you take the partial derivatives, and so this defines you the normal derivative. You take the partial derivative multiplied by the corresponding component of the normal derivative, take the sum. This is the normal derivative. That means derivative is in normal direction. It is coming out of the surface. You cannot define normal derivative for the function which is defined only on the surface, because this derivative is coming out of the surface. Normal is coming out. This is the derivative along the normal vector field. But altogether, this is also coming out of the surface. This is also coming out of the surface. This is incorrect definition of the tangential derivative. But the correct definition is this one. Because this dg vector, which gives this dg, is a tangential vector field. If you take, what is dg here? dg is the projection of our unit vector field. So, in the Euclidean space, you have this, how to say, canonical unit vectors. E1, which is 1 and zeros. This is the vector which has length 1 and is directed along the axis x1. And xeg is the vector, unit vector, which is directed in the direction of xg. of g coordinate axis. So you take such vector, or consider it here, and this is the vector, AG for example, and take the projection of this vector on this surface. So it means that in this place it will be the projection this one, this is dg. At this place projection will be 0, simply 0. dg is 0. Your projection is 0. What will be here? Here will be the projection the tangential projection. At this place, tangential projection will be, this is one, this is the vector itself, and the projection will be this one. So dg at this place is this one. So if you take such projection of your coordinate vectors, you will get dg, and they are tangential. Because if you multiply, what means tangential? If you multiply this vector by, you take the scalar product with the normal vector field, you will get 0. That means that these vector fields are tangential, and these derivatives can be defined correctly on this surface. And they play the same role on the surface as the usual partial derivatives in the Euclidean space. These are very nice derivatives. So then you have also the gradient of the function, which is exactly, you take first derivative of the function, last derivative of the function, you take this vector. This is gradient of the function. You can define also the divergence of the vector field. You take the first derivative of the first component, and the sum of these derivatives, you get divergence. So usual divergence and usual gradient, you know. Gradient I have written. This is the vector, which is derivative of function with respect to the first variable and so on, and variable. Oh, I have not written. Okay. And the usual divergence is the partial derivative, first partial derivative, nth partial derivative, and you take this sum of first component, the nth derivative of the nth component. So divergence and gradient. Now we have analog on this surface, and this is the full analog of the. There's defined very